Hello class. So on this video, we're still on section 3.5. Now we're finally going to go through the general process of finding a particular solution. This is after doing two examples. Okay? So I'm basically going to justify that this is the right way by showing that it worked in these two examples. It's not the best justification, but hopefully it's enough for you to believe that or see where, in a way, where this process comes from. Okay? So let's go back to the examples that we saw. So in the first example, the function on the left, on the right-hand side, was 2x, and our particular solution was ax plus b. So I'm going to write this here. So on example 1, our guess was, for the form of the particular solution, was ax plus b, and the right-hand side, it's going to denote by RHS, was 2x. On example 2, our particular solution was I think sine x is what I wrote, plus b cosine x, and the right-hand side was 2 times sine of x. Now let's see if we can see a pattern in the choices of particular solutions or forms of particular solutions that work and related to what was on the right-hand side of the equation. Oops. I don't know how I did that, but actually I like it. Let me try to highlight. So now related to this and to this. Okay. So looking at example 1, it looks like, or y sub p given by ax plus b satisfies the property that it contains all possible forms of, and let's give them this functions name. Let's call them f of x, so I can just call them, let's call them f of x. Here, let's call it f1 of x, f2 of x. Although I use g, let's call them g. I'm just trying to make sure that the notation is as consistent as possible. Let's call this one g1 of x. Let's call this one g2 of x. So now let me write as I say what I'm going to say. So notice that y sub p equal to ax plus b contains all possible forms or terms, all possible terms that come from derivatives of f1, including the zero derivative. So every time I'm saying derivative, remember that I include the zero derivative as the function itself. Oops, zero derivative. Why? Well, the function itself has 2x as a term. Okay, we have something that has a constant times x as a term. And then the first derivative has a constant, right? Okay, we have something as the only term. So we have something that is a constant, right, in our particular solution as well. Any derivative after that is 0, which is just a constant. So again, that's already included by the fact that we are including a constant term in our particular solution. And you'll see that this is also the case for example 2. So let's do it in another color. Let's use red. So I'm just basically going to write the same thing, and you'll see that it works. Note that y sub p equal to a sine x plus b cosine x contains all terms that come from or show up. So I'm going to use both languages. So whichever makes more sense to you. Contains all terms that come from derivatives of g2 of x, and I realized I wrote f1 on the previous one. I'm going to change it in a moment. Of g2 of x equal to 2 sine x. And so before I show you that that's the case, let me change this for g2. Oh, g1, sorry. Why is this the case? Well, think of all possible derivatives of 2 times sine of x. The derivatives are always going to alternate between sine and cosine, right, up to a constant, right? The constant might be 2, might be negative 2, might be 2, might be negative 2, right, etc. But the actual functions, they're always going to either involve a multiple of cosine or a multiple of sine. Both terms are included in our form of a particular solution. And this is basically the method that we're going to do. What we're going to do is, given the function on the right-hand side, whatever it is, our particular solution is going to be a sum of all possible terms that arise after taking derivatives of the right-hand side. Okay. And again, I show you this so you see that this works, and you notice that this is a pattern that's going on. So it's reasonable for us to check whether this process works. Now, it turns out that this is the right way to do it. I won't explain it 100%, but at least you see where the thinking comes from. Okay. So I hope that this is enough for you to realize this doesn't come out of nowhere. I can understand what the people that were coming up with this were thinking when they were doing this, and I see why it works. Okay. So now let's go ahead and write it in general. Right. So the general process to find y sub p. Okay. So let's start. So of course we start with a non-homogeneous ODE. So given a non-homogeneous, so I say it like that so I don't forget how to spell it, and I don't even know if I spell it right anyway. So given a non-homogeneous, I think I'm missing an O somewhere. Okay. So given a non-homogeneous second order linear, so linear ODE, right? And again, we know what with constant coefficients. Right, so with constant coefficients, and we know that this looks like ay double prime plus by prime plus cy equals g of x, where g of x is not equal to 0, because if it were, it'd be homogeneous, and we already know how to find the general solution. Right. Then, what's our choice for y sub p? Oops, sorry. Then, y sub p should include all possible terms that come from derivatives of g of x. And again, every time we have a term, we always have an undetermined constant in front, so that we have degrees of freedom to find the constants that work. Okay. With each term having an undetermined constant or an unknown constant, whichever language you like. So let me write both. An unknown or undetermined constant in front, so as a coefficient. And that's the process. That's the guess you're going to choose for y sub p. And again, we already saw 2 examples where so I explained it a different way, but it turns out that this was what we were doing all along. Right? We weren't doing it that way, but basically we would have gotten the same answer if we just looked at the right-hand side, g of x, looked at all possible terms that come from derivatives, and include those in the particular solution. Same with example 2. Right? It would have been this. We would have gotten the same particular solution, form, if we simply looked at the right-hand side. Ooh, where is it here? If we simply looked at the right-hand side and included in our particular solution, our form of the particular solution, all possible terms, with constants in front, as I mentioned, that arise or come from the derivatives. And that's the general procedure. So now you know how to find a particular solution. Once you know how to find a particular solution, then the general solution is simply the sum of the general solution of the homogeneous case and the particular solution, as stated in theorem 1. So I'm going to do one example here. I'm not going to call it an example because, I don't want to mess up my numbering with the next slide. But let's say, so suppose the right-hand side of so I should find a way to make this less, but second order non-homogeneous linear ODE. Linear, yeah, okay, I said linear. Of a second order non-homogeneous, should be a comma, non-homogeneous linear ODE is, suppose that we have the right-hand side, or g of x, being, let's see, let's do something interesting. So something like e to the t, x, sorry, e to the x times sine x. Right? So that's the right-hand side. Find a form for y sub p. Now, as we saw in the general procedure here, all we have to do is include all terms that come from derivatives of g of x in our particular solution. So let's take a couple derivatives of g of x and see what terms we get. Right? So the zeroth derivative, right, is just e to the x sine x. So we know we're going to have to include this term. Now g prime of x is, okay, so we're going to have to use the product rule, right? It's going to be e to the x sine x plus e to the x cosine x. This just comes from the product rule. Second, the third, let's just do one more, even though this is enough, and you'll see why. Well, let's do one more. So we take the derivative again. The derivative of e to the x sine x, it's just what's above. So e to the x sine x plus e to the x cosine x. Now we need the derivative of e to the x cosine x. Again, it's just the product rule. Now, hopefully, I do one more. Like I said, once we're at the first derivative, I already know all possible terms that are going to arise from derivatives. But I do one more so you see that this is the case. Okay? Now, notice that the second derivative, the first derivative, has terms e to the x sine x and e to the x cosine x. Think of what the derivatives of those two functions look like. The derivatives are always going to look like e to the x times sine x or e to the x cosine x up to constant, right? There could be a negative in front, as we saw here. But in terms of functions that arise without ignoring the constants, we're always just going to get e to the x sine x or e to the x cosine x. So just by taking the first derivative, I already know all possible terms that are going to arise from all possible derivatives. And this is what you want to do, right? Why? Because you don't want to take infinitely many derivatives, right? You want to see a pattern. As soon as you take enough derivatives to realize, okay, now I know that all terms that arise are going to be these ones, then you're done. You don't have to do any more. Okay, so I explain why I know that all terms that are going to arise are going to be either this or this with possibly a constant in front. So that's all I need to know for my particular solution. Okay? So the form of the particular solution is going to be always a constant in front. So a times e to the x sine x plus b times e to the x cosine x. And this particular solution satisfies that all terms that arise from derivatives of g of x are included in this particular solution. So in the next homework, I'll give you a bunch of these so you can practice. So you can just look at this example, see at the practice problems in the book. Right? And in fact, in the book, they have a table, which I don't like to use tables because if you memorize it wrong or if you forget, you're kind of messed up. So it's better for you if you understand how it works. But they do have tables in the book where they tell you, okay, if g of x equals this, then you need to use you need to use a particular solution that has this form. Right? So they have a table like that. But again, I think it's better if you just work through this all the time. Right? Just note that what you need is to include all terms that comes from derivatives. So look at your g of x, take as many derivatives as you need until you realize that, okay, these are all the terms that are going to arise, and then just include those in your particular solution. Now, this process is going to work always for second order non-homogeneous ODEs with constant coefficients with one caveat. And that caveat I'm going to address in the next video. But other than that one caveat, this is always going to work for finding a particular solution.